Welcome to our channel. In today's video, me John with FrabHacker we're diving deep into the groundbreaking LeNet 5 architecture, a pivotal development in the field of convolutional neural networks, CNNs. Developed by Yann LeCun and his team, LeNet 5 laid the foundation for many modern image recognition systems. It was specifically designed for handwritten digit recognition and has significantly influenced how machines interpret visual data. Throughout this video, we'll explore the architecture of LeNet 5, breaking down its various layers, from the input layer to the output layer, and discussing how each component contributes to the overall performance of the network. We'll also touch on the real-world applications of this architecture, including its role in postal services for handwriting recognition and its contribution to the development of early optical character recognition, OCR, systems. So, whether you're a student, a researcher, or simply curious about deep learning, stay tuned as we unravel the mechanics of LeNet 5 and its impact on the world of machine learning.
The paper we are discussing solves several major problems in pattern recognition. Let's explore the key challenges it tackled and how it paved the way for modern machine learning systems. Problem 1. Feature extraction. Traditionally, extracting features from images was a manual process. Handcrafted algorithms were needed to identify important patterns. But this paper introduced something revolutionary: gradient-based learning applied to CNNs. Instead of manually crafting feature extractors, the network learns the features directly from the data. This eliminates human intervention and vastly improves accuracy by allowing the system to learn from examples. Problem 2. Segmentation and recognition. Segmenting characters from a document, especially noisy images, has always been tricky. Most systems would make early segmentation decisions that often led to errors. But in this paper, the authors solved that problem with heuristic over-segmentation. Instead of committing to one cut, the system generates multiple hypotheses and evaluates them all in parallel, avoiding early mistakes and optimizing the overall recognition process. Problem 3. Time-consuming hand-truthing. Before this work, labeling segmented characters was a labor-intensive job. This paper introduced a way to train multimodule systems that optimize the performance globally. What does this mean? No more tedious, manual truthing. The system can improve recognition accuracy without needing thousands of meticulously labeled examples, saving tons of time and effort. Problem 4. Integrating system components. The paper introduced a unified framework that integrates segmentation, character recognition, and linguistic models. This avoids the need for individual heuristics for each task, making the system more efficient and robust. But that's not all. One of the major breakthroughs introduced in this paper is the Graph Transformer Networks, GTN. These networks globally train multiple modules, including segmentation, recognition, and linguistic models, all at once. This global training approach results in significantly improved performance, especially in real-life tasks like reading documents or checks. So, what makes this paper so important? It not only solved fundamental problems in feature extraction, segmentation, and manual labeling, but it also introduced a way to unify the entire process. The techniques presented here laid the groundwork for modern CNN-based systems that are used in everything from self-driving cars to medical imaging. LeNet 5 was groundbreaking in its time, but it had some limitations. For instance, Problem 1. Small architecture size. LeNet 5 was a shallow network with just 5 layers. As datasets grew larger, this small size wasn't enough to capture the complexity of modern data. Models like AlexNet and VGG solved this by introducing deeper architectures with more filters, allowing for much better performance on complex tasks. Problem 2. Overfitting on large datasets. LeNet 5 struggled with large, complex datasets, often overfitting. VGG and LeNet tackled this with smaller filters and more layers, effectively learning more nuanced features from data without overfitting. Problem 3. Limited receptive field. LeNet 5 could only detect small-scale features due to its limited receptive field. Enter LeNet with its Inception module, which introduced multiscale feature detection, allowing the network to capture both local and global features in images. Problem 4. Inefficient parameter usage. LeNet 5 underutilized its parameters, meaning it wasn't using its resources efficiently. ResNet came along with residual connections, which allowed the model to make better use of parameters and improve learning efficiency. Problem 5. The vanishing gradient problem. As networks got deeper, training became harder due to gradient loss. ResNet fixed this by introducing skip connections, allowing gradients to flow smoothly through the network, even in very deep models. Problem 6. No batch normalization. Training LeNet 5 was unstable, and convergence was slow. The introduction of batch normalization in models like AlexNet, VGG, and ResNet dramatically improved training stability and speed. Problem 7. Poor handling of high-resolution images. LeNet 5 was designed for small images like 32 × 32 pixels. But with high-resolution images, it fell short. VGG and ResNet took the lead with deep architectures specifically designed to handle larger images with much better accuracy. Problem 8. No transfer learning. LeNet 5 was limited to its specific task. Models like VGG and ResNet introduced pre-trained models that could be easily fine-tuned for a variety of tasks, opening the door to transfer learning. Problem 9. Inefficient resource use. LeNet 5 required a lot of memory and computational power. MobileNet addressed this by introducing depth-wise separable convolutions, drastically reducing computation while maintaining accuracy, making it ideal for mobile and embedded devices. Problem 10. Single task focus. LeNet 5 was designed for classification, but modern needs go beyond that. YOLO and Mask RCNN expanded the field to include object detection and segmentation, giving machines the ability to not only classify but also locate and understand objects in images. LeNet 5 contains the basic building blocks of deep learning, the convolutional layer, the pooling layer, and the fully connected layer. These components form the core of many modern neural networks. LeNet 5 is made up of 7 layers in total, not including the input layer. Each of these layers contains trainable parameters, and each layer extracts features from the input using convolutional filters. Each layer in LeNet 5 includes multiple feature maps. These feature maps are created by applying filters to the input. The filters detect important features in the data, such as edges or patterns. Once extracted, the feature maps are processed by multiple neurons, learning deeper and more complex representations of the data. Let's break it down further. The convolutional layer applies a filter to the input, scanning across the image to detect patterns. Then, the pooling layer follows, which reduces the size of the feature map by taking the most important information, helping the network focus on key features while reducing complexity. LeNet 5 may seem simple compared to today's models, but it introduced core principles that are still used in more complex architectures. By mastering these basic modules, you'll have a solid understanding of how deep learning works from the ground up. Let's explore how each component of this classic neural network works together to process and classify images. We start with the input layer. LeNet 5 takes in an image that's 32 × 32 pixels with just one feature map. This layer doesn't apply any filters, it simply feeds the image into the network. Next up is the first convolutional layer. It creates 6 feature maps, each sized at 28 times 28. The filters applied here are 5 times 5 kernels, and they slide across the image with a stride of 1. The activation function used is tanha, which helps the network learn nonlinear features. After convolution, we move to the first average pooling layer. It reduces the size of each feature map from 28 times 28 to 14 times 14. The kernel size here is 2 times 2 with a stride of 2, and again we use tanha as the activation function. Next is the second convolutional layer, which increases the complexity by generating 16 feature maps at 10 times 10 size, still using a 5 times 5 kernel and a stride of 1. Tanha continues as the activation function. We then move to the second average pooling layer. This layer reduces the feature map size from 10 times 10 to 5 times 5. The pooling operation uses a 2 times 2 kernel with a stride of 2, and of course, we still use tanha as the activation. In the final convolutional layer, we have 120 feature maps, but each is reduced to 1 times 1 by a 5 times 5 kernel with a stride of 1. This essentially compresses the output before it's passed on to the fully connected layers using tanha activation. Now we hit the fully connected layer. This layer has 84 neurons, and like previous layers, it uses the tanha activation function. Finally, we arrive at the output layer. This layer contains 10 neurons, corresponding to the 10 possible classes for digit recognition. The activation function here is softmax, which ensures the output is a probability distribution across the classes. To recap, LeNet 5 processes input through layers of convolutions, pooling, and fully connected neurons, extracting key features and reducing complexity at each step. This architecture is simple but incredibly effective, laying the foundation for modern deep learning networks. First up, we have an input image that's 32 times 32 pixels. The C1 layer applies 6 convolution kernels, each sized at 5 times 5. After the convolution operation, we end up with 6 feature maps, each of size 28 times 28. Now, why does the output feature map shrink to 28 times 28? Simple. It's calculated as 32 to 5 plus 1 is equal to 28. This is how convolutional layers reduce the spatial dimensions while extracting important features. The C1 layer has 28 times 28 neurons for each of the 6 feature maps, giving us a total of 28 * 28 * 6 neurons in this layer. Now, let's talk about the trainable parameters. Each convolution kernel is 5 times 5, and each kernel also has a bias. So, for 6 filters, we have a total of 156 trainable parameters, that's 5 times 5 plus 1 per filter, multiplied by 6 filters. Here's where things get interesting. Even though we only have 156 parameters to learn, the total number of connections in the C1 layer is massive, 122,304 connections in total. This is calculated as 5 times 5 plus 1, * 6 * 28 * 28. That's because each pixel in the feature map is connected to a 5 times 5 patch of the input image, plus a bias, across 6 feature maps. But how can we have so many connections while only learning 156 parameters? It's all thanks to weight sharing. The same set of weights is applied across different parts of the input image, making the learning process much more efficient without compromising on performance. To recap, the C1 layer applies 6 convolution kernels to a 32 times 32 input image, producing 6 feature maps of size 28 times 28. With 122,304 connections, but only 156 trainable parameters, this layer is highly efficient and essential for extracting low-level features from the input. That's a quick look at how the C1 layer in LeNet 5 works. We are diving into the S2 layer of LeNet 5. This is the pooling layer, also known as the downsampling layer. Let's break it down and see how this layer helps reduce the complexity of the data while preserving key features. The input to the S2 layer is a 28 times 28 feature map, which was created by the previous convolutional layer. Pooling is performed using a 2 times 2 sampling area, which reduces the size of the feature map by half, giving us an output size of 14 times 14. Here's how pooling works. For each 2 times 2 region, the 4 inputs are added together, then multiplied by a trainable parameter, and finally, a trainable offset is added. The result is passed through a sigmoid function, which scales the values. The S2 layer produces 6 feature maps, each sized at 14 times 14. This is because the input size of 28 times 28 is downsampled by a factor of 2. The result is smaller, more manageable feature maps that retain the important information from the convolutional layer. In total, the S2 layer has 14 times 14 neurons per feature map across 6 feature maps, giving us 14 * 14 * 6 neurons. Despite this reduction, the layer still maintains 5,880 connections. Each pooling operation involves 2 times 2 plus 1 connections multiplied by 6 feature maps and 14 times 14 neurons. The S2 layer has 12 trainable parameters. Each 2 times 2 pooling kernel has 2 parameters, one for the weight coefficient and one for the offset. With 6 feature maps, that gives us 2 times 6 equals 12 trainable parameters in total. So to sum it up, the S2 pooling layer downsamples the input from 28 times 28 to 14 times 14 for each of the 6 feature maps. With only 12 trainable parameters and over 5,880 connections, this layer reduces the complexity of the network while retaining important features from the input. That's a quick look at how the S2 pooling layer works in LeNet 5. Now we'll be exploring the C3 layer of the LeNet 5 architecture, a crucial convolutional layer that helps extract even more complex features from the input images. Let's break it down. The C3 layer takes input from all 6 feature maps, or combinations of those maps coming from the previous S2 layer. Each feature map in C3 is designed to connect to these feature maps, creating a new set of feature combinations. Now, let's talk about the specifics. The convolution kernel size used in this layer is 5 times 5, and C3 generates a total of 16 output feature maps, each sized at 10 times 10 pixels. This is calculated using the formula 14 to 5 plus 1 is equal to 10, which accounts for the reduction in size due to the convolution operation. What makes this layer special is how it connects to the S2 feature maps. The first 6 feature maps in C3 connect to 3 adjacent feature maps from S2. The next set of 6 feature maps connects to 4 adjacent feature maps, while the following 3 maps use 4 non-adjacent feature maps from S2. Finally, the last feature map takes inputs from all 6 feature maps in S2. Now, let's dive into the trainable parameters. The total number of parameters in the C3 layer can be calculated like this, times. For the first 6 feature maps, 6 * 3 * 5 * 5 plus 1. Times. For the next 6 feature maps, 6 * 4 asterisk 5 asterisk 5 plus 1 times. For the following three feature maps, 3 asterisk 4 asterisk 5 asterisk 5 plus 1 times. And for the last feature map, 1 asterisk 6 asterisk 5 asterisk 5 plus 1. When we add them all together, we find that the C3 layer has a total of 1516 trainable parameters. But that's not all. The number of connections in this layer is calculated as follows: 10 asterisk 10 times 1516 equals 151,600 connections in total. This demonstrates the high complexity of the C3 layer, allowing it to effectively combine features from the previous layer. To recap, the C3 layer in LeNet 5 operates on input from the S2 layer, applying 5 times 5 convolution kernels to create 16 feature maps, each measuring 10 times 10 pixels. With 1516 trainable parameters and 151,600 connections, it showcases the powerful feature extraction capabilities of convolutional networks. We are going to explore the S4 layer of the LeNet 5 architecture, which serves as a pooling layer for downsampling. Let's break down how this layer works and what it contributes to the network. The input to the S4 layer consists of 16 feature maps, each sized 10 times 10 pixels. This layer continues the downsampling process using a 2 times 2 sampling area. In the S4 layer, pooling is performed by taking 4 inputs from each 2 times 2 area. These inputs are added together, multiplied by a trainable parameter, and a trainable offset is added. The output then goes through a sigmoid function for scaling. As a result of this pooling operation, the output feature map size becomes 5 times 5 pixels. This is calculated as 10 halves, effectively reducing the size while retaining important features. Now, let's look at the number of neurons in the S4 layer. Since we have 16 feature maps, each of size 5 times 5, we end up with a total of 400 neurons in this layer, calculated as 5 asterisk 5 asterisk 16. Next up are the trainable parameters. In this layer, we have 32 parameters total, which come from 2 trainable parameters for each of the 16 feature maps, one for the weight and one for the offset. Now, let's calculate the total number of connections in this layer. The formula is 16 asterisk 2 asterisk 2 plus 1 asterisk 5 asterisk 5, which results in 2000 connections. This reflects the high connectivity of the S4 layer as it processes the pooled data. To summarize, the S4 pooling layer takes 16 feature maps of 10 times 10 pixels and downsamples them to 16 feature maps of 5 times 5 pixels. With 400 neurons, 32 trainable parameters, and 2000 connections, it effectively reduces complexity while preserving essential features from the previous layer. The C5 layer takes input from all 16 unit feature maps of the S4 layer. This means every feature map in C5 is connected to all feature maps from the previous layer. In this layer, the convolution kernel size is 5 times 5, and we use 120 convolution kernels. Since the size of the feature maps from S4 is 5 times 5, they match the size of the convolution kernel perfectly, resulting in an output feature map size of just 1 times 1. This means we get 120 output feature maps, each producing a single value after convolution, making it a compact representation of the input. Now, let's talk about the trainable parameters and connections in the C5 layer. The total number of trainable parameters is calculated as follows: 120 asterisk 16 asterisk 5 asterisk 5 plus 1 is equal to 48,120 parameters. This formula accounts for the connections from each of the 16 feature maps, with each one contributing its own parameters.
Now with John you will explore the layer F6 onwards. The input to the F6 layer is a 120-dimensional vector that comes directly from the C5 layer. This vector contains all the features extracted and condensed from the previous convolutional operations. In the F6 layer, we calculate the dot product between this input vector and the weight vector associated with the layer. After that, we add an offset, also known as a bias, to the result. Finally, the result of this calculation is passed through a sigmoid function. This activation function helps to map the output to a range between 0 and 1, making it suitable for classification tasks. Now, let's talk about the trainable parameters in this layer. The total number of parameters can be calculated as follows. 84 asterisk 120 plus 1 equals 10,164. This includes 84 neurons in the F6 layer, each connected to the 120 inputs from the C5 layer, plus an additional parameter for the bias. We're going to dive into the output layer of the LeNet 5 architecture, which plays a critical role in the network's ability to recognize digits. Let's explore how it works. The output layer is also a fully connected layer, consisting of 10 nodes. Each node corresponds to a digit from 0 to 9. So, if the value of node 3 is the highest, the network recognizes the input as the digit 3. In this layer, a radial basis function, RBF, network connection is utilized. Let's say XXX represents the input from the previous layer and YYY represents the output of the RBF. The calculation of the RBF output is essential for digit recognition. The value of the RBF output, denoted as 3, is determined by the bitmap encoding of the digit 3, where 3 ranges from 0 to 9. Each JJJ corresponds to different pixel values. The closer the value of the RBF output is to 0, the closer it is to 3. This means that the recognition result from the network input is likely the digit 3, correlating to its ASCII encoding. Now, let's discuss the parameters in this layer. The total number of parameters and connections is calculated as follows. 84 times 10 is equal to 840 parameters. This comes from having 84 neurons in the previous layer, each connected to the 10 output nodes. To recap, the output layer of LeNet 5 consists of 10 nodes for digit recognition. It uses radial basis function connections to determine the output based on the closeness to the corresponding ASCII values. This layer has a total of 840 parameters and connections, allowing it to effectively classify the input as one of the digits from 0 to 9. That wraps up our exploration of the output layer. We're discussing some fascinating applications of technology in the field of handwritten text recognition, particularly in postal services, signature verification, and the pioneering of optical character recognition, OCR, systems. First up, let's talk about handwritten digit recognition in postal services. Postal systems around the world receive millions of letters and packages every day, many of which are addressed by hand. Using advanced digit recognition technology, postal services can automatically read handwritten addresses and postal codes, significantly speeding up the sorting and delivery process. This technology not only improves efficiency but also reduces human error. With accurate handwritten digit recognition, postal services can ensure that mail reaches its destination on time, making the entire system more reliable. Next, let's move on to check signature verification. In financial transactions, ensuring the authenticity of a signature is crucial. Handwritten signatures serve as a personal identifier, and advanced recognition systems can analyze and verify signatures on checks and documents, preventing fraud and ensuring security. These systems can compare a signature against a database of verified signatures, assessing characteristics like stroke order, pressure, and overall shape to determine if the signature is genuine or forged. Lastly, we can't overlook the pioneering work done in optical character recognition, OCR, systems. Early OCR systems laid the groundwork for today's sophisticated text recognition technologies. They enabled machines to read printed and handwritten text, opening up new possibilities for digitizing documents and automating data entry. Today, OCR technology is utilized in numerous fields, from document scanning and archiving to translating handwritten notes into digital text, showcasing its versatility and impact. In summary, handwritten digit recognition has revolutionized postal services by improving efficiency, while signature verification enhances security in financial transactions. Additionally, the early development of OCR systems has paved the way for the text recognition technologies we use today. Thank you for joining us on this deep dive into the LeNet 5 architecture. We hope you found the insights into its design and applications valuable. If you enjoyed the video, please give it a thumbs up and share it with your friends or anyone interested in learning more about deep learning. Don't forget to subscribe to our channel for more content like this. Your support helps us create more educational content and explore fascinating topics in the world of artificial intelligence. So, signing off, John with Farbhacker. Thank you, viewers.